Hey everyone, moving on with our question types, we have the following question type. We have the same curve again as the previous question type, and now we want to show that minus 1 lies on this particular line, kx plus k minus 1. I think it's quite easy, I don't have to go through it, you can try it out yourself, right? But essentially now, the main part of this question type is this idea. After showing that minus 1 lies on the line, you want to hence find the range of values of k, where kx plus k minus 1 equals to the above curve, has two real roots. So, well, first thing first, find where's minus 1. And we know that it must lie on the vertical asymptote as equals to minus 1. And although it's insignificant, in this question, it lies on the oblique asymptote as well. But what's so significant about this point is that it lies in between the top and the bottom curve, and that will actually affect the way, or rather influence our way of solving this question. Now first, range of values of k is what we need to find. Ask yourself, what is the significance of the value k? We have the equation y equals kx plus k minus 1. And we notice that k is the coefficient of x, which means that it is the gradient of this particular line. So this question is converted from finding the range of values of k, reworded to what is the range of values of the gradient such that this particular line kx plus k minus 1 that passes through minus 1 intersect the curve twice. That is how you can rephrase your question, and that's what you should be thinking. So now, first idea. We are playing the gradient, so what does it do? We know that whatever the value of k is, minus 1 will be a point. So we're just going to rotate the line, well, about the point minus 1. Alright? So I think quite simple. Okay? And this will be the idea. Now, next step. How to get to intersection points? Usually there are two ways, or rather there are not just two ways, rather there are many ways to obtain two intersection points. But in this case, there are only one way. If you notice, because the point that is kind of permanent regardless of the value of k is in between the top and bottom curve, the line must intersect the top curve and the bottom curve once each in order to give you two real roots. And there's no other ways of obtaining two real roots. Because if you look at it, right, when you rotate the line about the point minus 1, it's just going to intersect the top and bottom curve once each at best, right? Of course, that's about it, right? Now, it's only coincidental that this line kind of can become the oblique asymptote y equals x. But let's see if I were to change the question and have this line instead, you notice that there are some cases where you only intersect the curve once, right, at the bottom, but then not intersect afterwards, or intersect twice, alright? So only in this question where it's only two times or none. Now, back to this question, two real roots. So if you notice, gradient can be positive or negative, right? So let's start the negative. I think it's quite obvious. And we're going to rotate about the point minus 1, the green point. So if you start with the negative gradient, you notice that, well, we're not going to catch any ball with the negative gradient until, even at negative infinity, where it's basically almost parallel to the oblique, or rather the vertical asymptote, and it still not give you any roots. Alright, so k can't be negative to give you two roots. Neither is it 0, and you notice that, well, it can't be from 0 to 1 either. Right, because from 0 to 1, again, you catch nothing. At 1 is the asymptote, right? It's parallel to the asymptote, and either intersects 0 times or once. In this case, it is 0 times because, again, coincidentally, this line can be y equals to x when k equals to 1. But when we increase the k past 1, you know that we're going to intersect the top and the bottom curve once each, and that will give us two real roots. And if we continue increasing k, same thing, right? Top, bottom once each. And of course, it will never become well, parallel to the vertical asymptote, because there's really no such thing. All right, so very simple. The answer for this question is simply k bigger than 1. All right, having a gradient that's greater than 1. Of course, if I have to change the question, let's say we change a point. Let's say we have a new point for the curve, or rather for the line. Let's say I mark it off red. Let's say we have the point over here and the line passes through this point instead. Now you notice that in order to get to the roots, there are actually a few ways, right? One way is this way. You notice that we intersect the bottom curve twice, like this, like this, like this, like this, and of course to the turning point. Or like this, right? At this point is still intersecting, but once you get a line that's parallel to the oblique asymptote, you notice that this part of the curve, or rather the line, will never intersect the curve at this part, right? Because we know that, well, the idea of oblique asymptote and the graphical representation is that the curve will never ever touch the oblique asymptote, but will get quite close to it. So it will never ever touch the red line as you've seen from just now. Likewise, because of that, we will not be intersecting the top as well, right? The curve on top. But when the gradient becomes greater than 1, then we will then start to intersect the top. And again, we won't intersect the bottom, right? Because now the line diverges away from the curve, from the bottom curve to be more specific, and you never ever intersect at that particular point again. All right, so that is the whole idea of discussion type, manipulating the gradient of this new line and figuring out how X numbers of roots might be obtained. And again, pay attention to the oblique asymptotes. Idea of parallel also comes into play, and also the turning points, and maybe for some questions, intercepts, right? Let's say do you only want positive roots or negative roots, that will also come into play. All right, so take note of discussion type. Quite easy to score if you think about it hard enough.